Hello. Good evening, everyone. Navneet here. So, Abhi, can you hear me?
Yeah.
Okay. So, yeah, welcome everyone. Sorry for the delay. Like we are just setting up the YouTube stream and all. So, sorry for the delay. So, welcome to the today's webinar on Q learning, deep Q learning with TensorFlow. This is one of the exciting topic which I have untouched from the events from our communities. Like so far, the past events are focused on machine learning and deep learning. So, only about a lot of things about GANs and CNNs and stuff and all. So this is one new area, reinforcement learning, which is untouched. So today we have Abhinandan. He's an Kaggle master and he is also doing a lot of stuff in AI and he is solving a lot of problems in Kaggle and he is one of, to be say, like a perfect person to handle this webinar. He has done a little bit of reinforcement learning also. So today's webinar will be an intro to the reinforcement learning with an implementation of deep equal learning algorithm in TensorFlow, right? So yeah, it will take for maybe 1 hour, 1 hour 20 minutes the session. After that, we will have a Q&A so that you can ask your questions and you can clarify your doubts in that last few minutes, right? Yeah. With that, welcome Abhinandan once again. You can take over the session.
Thank you, Navneet. Welcome, everyone. Thank you so much for joining. And this session is going to be on deep reinforcement learning. So there are a lot of things that go before you learn deep reinforcement learning. So we would touch upon some of these concepts and uh, really make sure that we understand these and then move on to the code. So, okay, to start off, this is the plan for the day. So
Abhi, can you be a little bit more louder so that it will be
yeah. Okay.
okay?
So this is the plan for the day. So we'll define what is reinforcement learning formally, and then uh, talk about one of the most fundamental concepts of reinforcement learning, Markov decision process, and then Q learning. And we're going to figure out where this Q came from. Many people were asking me like, what is Q learning? Is it deep learning or what is it? So uh, Q learning is an algorithm that's used in reinforcement learning. So uh, we'll go over this step by step, and it will be like a story unfolding over time, and you would be able to at the end of the day make sense of how this algorithm actually works. So you can post your questions you can go to slide.do, go to this website, and if you enter this code like 91439, you'll get to a page where you can post your questions. uh, all sort of questions that you have, you can post there, and we'll try to answer. Okay. So So let's get started actually. So reinforcement learning is one of the most exciting fields of machine learning right now, and it is also one of the oldest. Actually, the origins of it trace back to around 1950, 60. The idea was there all the time, but just now we have figured out how to do it, and with the rise of compute power, we are able to uh, make use of these algorithms and make it actually work and solve very interesting problems like um, this actually took off recently in 2013 when DeepMind showed the whole world that uh, a- an algorithm can play any Atari game at the level of better than any human. An Atari game is like a basic game that we used to have in the early 2000s, 1990s, something like that. It would be like you'd move a pawn, the ball would jump over and things like that. It's very basic, but uh, to be for the machines to be able to play the game at level that's better than humans is actually uh, completely changed the way everyone was thinking about reinforcement. And since that moment, we've seen excellent progress in this field. It's actually very new, so the resources here are very limited, and there's a clear shortage of good resources online to learn this stuff, especially when it comes to practical reinforcement. There are very little tools that would help you to go from zero to like an intermediate stage where you can do that for machine learning. There are plenty of tutorials, but for reinforcement learning, it's not. You need to be a lot more self-taught here, read a lot of books and like that. You can learn, but Let's move on to the formal definition of reinforcement learning. This is the definition that I took over from Wikipedia. What it says is other, unlike any other machine learning paradigms, here we have an agent which is trying to move in an environment, trying to take actions, and influencing the environment, and the environment gives back a reward. And then um, the main idea behind this is the agent trying to do some actions in such a way that it maximizes the cumulative feedback and reaches a goal. So if that doesn't make sense to you right now, then that's completely fine, because we are going to break this down into uh, many pieces and then just inspect in every possible way to make you understand. So this diagram is very very repetitive in the field of RL. This shows what RL is doing clearly. So now we're going to jump more into the representation. How do we represent a state? So that's st. T means time. So at a specific point in time, let's say its current time is denoted as t. So s of t means the state that we're in right now. So if let's say the agent takes an action, that's the action is denoted with a. When did it take an action? That's denoted by t. So after taking an action, the environment gives it a reward, and then you move over to the next step. So um, I'll explain this with a very simple example right now, so you can understand this agent, environment, state, action, reward, and everything better. So let's say you're the agent. So what better way to imagine an agent than you, right? So let's say you're an agent, or you're inside a room, and the goal for you is to reach the door. You're inside a room. The goal is to reach the door. So uh, let's say you're in some corner, so that getting to the door is a little bit hard. So you're the agent. So the learner in an environment, the environment here is the room, and you're the agent. And the state is, let's say you're standing right now. You didn't make any action. This is the starting state. You just didn't you you're just starting out. So that's called s of t, and this will change over time when run in a loop like fashion. And let's say you move a couple of steps forward, and that is an action, right? That's an action. You're moving forward, moving right, moving left, back, anything, that's an action. So in this environment, it is pretty damn clear that you can move in like four directions, or even eight. So there might be eight actions that you might be able to take, but the environment gives you a reward. This reward is the thing that's mostly not understood. What is a reward actually? How do we represent reaching a goal in terms of a single scalar reward? So yeah, it could any goal can be represented in form of a single scalar reward. That's the main idea behind RL. If this is not true, then many RL applications won't work. And there is a hypothesis. There is an hypothesis in RL called reward hypothesis, where it's described that all goals can be described by the maximization of expected cumulative reward. So what that means is, uh, you get a reward for each action, and the cumulative sum of these rewards can be described as a goal. Whatever goal you choose, it could be described as a single scalar value. So this is a reward for, in this case, like reaching the door. Signal might be like when you move closer and closer to the target, that the target is your the goal state or target, whatever you say. The target is the goal. Then when you move towards the target, you'll get a positive reward. If you move away from this, or if you move sideways, there is a there is a negative reward. So that way we can represent the, this is a very simple environment, and the agents can uh, move around, figure things out, and identify where it gets the right reward and move in certain direction. Our goal is to design this agent in such a way that it can it can maximize this cumulative reward thing that I was talking about previously. So you might ask why this reward could be a single scalar value, especially when you consider fact that when you make an action, you get a good reward for one. For example, if you're in an office, you do an action and you get appreciation from your boss, but your friend completely hates you for what you did. Then these are relative. So one action can lead to two different consequences. So these consequences, how can it be, how can these consequences be represented in form of a single reward? The idea is that when you take these actions in sequence, like many actions you might be taking, like let's say you take about 10 actions, and then these feedback signals can be independent. you know they might be like they might be happening over time. You just the goal is to your goal is to maximize the reward at the end. uh, uh, when we compare each and every reward at the scale, like for comparing, in the end everything leads up to one single scalar reward. So that's the main idea why there is a hypothesis called a reward hypothesis, where that's described the single scalar reward is good enough to represent the entire uh, goal. All right. So I hope that made sense, because this is like a really important thing in RL rewards. So this is another example here. So let's say you're designing an agent. The agent in this case is this blue brain thing that we're going to design. So this is not going to be like a blue brain thing in reality. So it's just going to be a software program, something like that, or a robot trying to walk in a robot trying to walk in the real world, or it might be a simulator. It might be a virtual robot trying to walk in a virtual world. It could be anything. So in this case, it is a real world. Your agent is going to play PlayStation, so you can take actions on the environment using the joystick, obviously. And then the console. Um, the console is actually your state, your environment itself. It decides what happens next. So you don't get the control over the environment. That's also an important thing in all RL. So the agent can influence the environment, but it cannot control the environment, right? So what happens is, if we should start off from here, not from here. So uh, if this is an observation from the state, this is the current state you're in. This guy is trying to kick this ball to it might be anywhere, here, anywhere. If you're the goalkeeper agent, then let's imagine you to be that goalkeeper, and you want to save this all the time. uh, let's imagine this to be the most dreadful PlayStation game ever, where you only try to get to control the goalkeeper. So when he hits the ball, there are several possibilities. You can move left towards the bottom, towards the bottom, or towards the. You can jump up, depending on where he's going to hit the ball. If he hits the ball in top left hand corner, then there is no point in diving to the bottom left. So there might be four actions: top left, bottom right, top left, top right, bottom left, bottom right. So this is an observation. First, your agent the observes the environment, and then it gets to take an action. So it could be random, it could be a very good action. It could be most of the times it is not possible to explain that way. So let's say your agent is a random agent, so it takes random action, and then you get back a reward based on what action you take. This reward might be like, if you there are only two possibilities here: either you save, either you don't save. So when you save, the reward might be a large positive scalar value, and or it might be just a positive scalar value, depending upon what you're trying to solve. And when you don't save the world, it might be a large negative reward. So that way we have actually represented the way in which the uh, which the agent has to take action in order to maximize these rewards. When the agent tries to get more positive rewards, we would see an active learning curve there for the agent. So this is the general formulation of reinforcement learning. This is everywhere. Observation, action, reward. These are the fundamental building blocks of reinforcement learning in general. So this is also one of the most important concepts. You need to understand the differences between RL and other machine learning paradigms. So here everything is based on a reward signal. It is not, uh, comparing it with supervised learning. There you have a supervisor that tells you what, or if your actions are good or bad, or how good it might be. It depends. Let's say it's just like good or bad, then your supervisor can tell you this action here. In RL there is nothing like that. uh, there is no supervisor, and it is completely not related to unsupervised learning. If there is no the agents, or sorry, not, there cannot be anything that can itself influence the environment in any of the machine learning paradigms that we observe. That's one of the main concepts that differentiate uh, reinforcement learning with other machine learning paradigms. Let's move to the next one. So the feedback, although this feedback, we get a feedback, so but it is not instantaneous. So it might be thought of like you're doing some action, sequence of actions. Then the fourth action you take gave you a good positive reward, and you moved, and this has influenced you in moving in a particular way. And then because of you doing certain action that has led to you getting this large positive reward, in future it might lead you to a catastrophic negative reward. So there is no instantaneous way to tell you if your actions are good or bad. You have to explore the environment and figure that out. That's the main idea here. And the data we encounter in RL is not IID. Definitely not IID. uh, IID means independent and identically distributed. So this this is definitely not IID. Why? I'll say, uh, for example, with an example of tossing a coin. When you toss a coin, let's say you get heads on the first try. The second time you toss it again, you get tails on the second try. So does you getting heads on the first time has any influence on you getting tails for the second time? Not really, because these are independent from each other. So that's exactly what is meant by independent. So identically distributed means, let's say you take a couple of coins, or let's even imagine that you take a whatever coin. In any coin there would be like a head or tail, so the distribution is going to be similar. 50% of the time, probability distribution, sorry, the 50% of the time there is a possibility of getting heads, and 50% of the time there's a possibility of getting tail. So that way, even if you try to gather 100 coins, it's going to be the same. It's going to be identically distributed. So when it is independent and identically distributed, the data is excellent for machine learning. Most people actually don't understand IIDs. So what IID in data means is, let's say you're having a supervised learning, you're doing a supervised learning task where you're going to detect diabetes, or if a patient has diabetes or not, based on several features that you obtained from the doctor or someone. Okay, it could be anything. So uh, there might be about 10, 15 dozens of features, and uh, for every sample there will be a value, like if that person actually had diabetics or not. So let's say your data, you're observing the data. You're just you're now seeing the first row of the data, and it says this person has diabetes. Okay, so you come over to the next one and you see this again, and this person doesn't have diabetes. Does the first person having diabetes has any effect on the second person? not having diabetics? No, these are independent from each other. If they were dependent, although this might be dependent for some tasks like time series problem, where you might think like the previous actions uh, are the only ones that decide the next ones. Even in that case, there can be several features that impact these, that can for example, in the stock market, there may be several factors that influence these changes rather than just the previous day or previous months. I think we're getting the point here. So even in data, this independence can easily be understood, but identically distributed is somewhat difficult to understand. For me, I think most people struggle there to understand this concept. So when there has to be some distinct differences between the features that's making you uh, say that one person has diabetics and the other person doesn't. So if this kind of a probability, if this is represented like a probabilistic distribution, then if everything is unidentical in nature, everything is mixed up, everything is random, there is no way we can actually come to a conclusion. All right, just like the coin toss ball. For example, this might be like you're taking a dice. Okay, let's move on from the coin problem and now discuss about something a little bit different, like a dice. So this dice has six sides. Dice have six sides. So you're taking the first dice, and this is independent from another. You're taking another dice, which is very different from the normal dice that you observe. And this dice is weighted dice. So weighted dice means, let's imagine this to be literally made changes to the dice in such a way that 1 and 6 come out more often than the rest. So like it has more probability, then the probabilistic distribution of the first and second thing is different. So there is no way we can actually identify it as identically distributed. So if it is not identically distributed, it's going to be one hell of a task for machine learning. So that's why uh, RL is kind of a problem where we have an environment, everything is stochastic in nature. In RL, if you cannot, RL itself is stochastic. The environment, the actions, everything is stochastic. Our goal is to make sense of this randomness and build an algorithms to adapt to the change or observe something and leverage that to maybe reaching a goal. So I think these are the differences from of reinforcement learning from the rest of the machine learning paradigms. There is also another difference. I think I touched upon this. So there is also another difference that I think I didn't add here. So here the agent gets to influence the environment. Does this happen anywhere in any other machine learning paradigm? I don't think so. So the agent doesn't get to directly influence the environment it's in any other paradigm. It's here. It's pretty clear. Okay. So Markov decision process is very important to understand reinforcement learning. It is one of the most fundamental building blocks, as I mentioned here. So what this means is it can be interpreted in different ways. So I'll just go in a few ways that I understand. So if you already have some experience in Markov chains and things like that, this certainly looks familiar to you, right? So uh, what this means is, let's say you're in state s of t, and the next state s of t plus 1 is fully dependent on the state that you're in. Okay, that's exactly what this probability being a state, and the next state is dependent on the first. This all this trying to say is the next state is fully dependent on the first state. What this is trying to say is the next state is dependent on every single states that have been seen previously. So what this equal to sign means here is, what this equal to sign means here is the rest of the information in the past history of all the states is irrelevant for to actually, like it's not yeah, this is exactly what I was trying to say. The current state is a sufficient statistic of the future. The past becomes irrelevant. It might be that way, or it could also be understood in a way that, sorry, it could also be understood in a way like whatever actions you've done in the past, whatever states you've been in the past, if all that has summed up to this particular state that you're in, then that is uh, good enough to estimate where you will be next. Okay, that's also a way of interpreting Markov chain. This is absolutely must to understand. We are going to build on this Markov state. So next we move on to Markov process, which is very similar. So now that we can we have defined the probability of transitioning from one state to another. Now we can map it down for every single state action, every single state path, and then like this is the state that you're in, and S prime is the state that you would transition to. Then it could be denoted as it could be denoted like this. So what it means is like like a probability matrix. So now you have everything down. So yeah, you have the probabilities for of transitioning from one state to another. So that's what Markov process means. This is also memoryless because we discarded everything about the past, right? That's why it's called memoryless. So the P here is transition probability, the probability that you would transition from a state S to state S prime. That's the transition probability. Based on, if we take all of these transition probabilities, we can build out a probability matrix, transition probability matrix. That's what it's trying to say. So we have gone from Markov state now to Markov process. Now what how what's the probability of transitioning from one state to another. Now the next one is Markov reward process. Uh, I didn't tell you why we are going through all this. So Q learning stems from steps back to a lot of concepts. So these are one of them. Markov reward process is one of the most important ones. Markov decision process comprises of this Markov state, Markov property, and the reward process. So let's try to understand this thing here. This equation in here. What it's trying to say g of t, that means the return that you would get from a state. So the return, the immediate return, so r of t plus 1 is the immediate return that you would get, and then t plus t, that's very intuitive, right? That's the subsequent returns that you are going to get. So this, if this is like this, then it's going to go over till infinity. So we add another parameter here like gamma. So this gamma is called the discount factor. So why do we need this discount factor? We will try to understand in a much more much different way. Let's say your agent is an animal and it's trying to graze the fields, for example. So the point here is why is immediate rewards greater than future rewards? What this trying to say, this gamma value will decay over time. So and then your future values would lose. This is between 0 and 1, by the way. I didn't mention that. This gamma values between 0 and 1. This generally in RL, the discount factor will be 0.95, 0.9, 0.98, something like that. This is also a hyperparameter here. So why the immediate reward that we're going to get is more important than the future rewards? So the main idea behind having such thing in place is like if you do what you do right, then you would end up in the right goal. So that's something we can control, but we cannot control what's going to happen in the future. That's going to lead us to infinity, and we might not be able to converge in machine learning perspective. That's exactly what they say. So that's why current reward is more weighted than whatever that comes next. So a low gamma means to myopic evolution. Low gamma means every single reward are the same. A high gamma leads to myopic evolution. Low gamma means it just completely waste the value of every single reward, and then this this weights every single reward equally. And this is a good hyperparameter for us to play with. Like this is not, I think this is unique to RL. This is nowhere else in machine learning. Okay, this blue thing is exactly what this is trying to say. This should make sense to you if you understand what I just told you. So now that you understand what is a return, we can calculate the value of being in a state. You know, now you know you're following a goal g of t, then if you're in a current state, yes, and then all the future rewards might come up to if you reach the goal or not. Now that you know that, you can calculate the value of being in every single state. This takes a little bit of time to kick in, but this trust me is it's going to be a lot easier. So v of s is the value function. Um, what the value function essentially means is the expectation of reaching a goal state given that you're in a current state. All right, this is very straightforward. The expectation of reaching a goal state given in the current state. So now you can calculate the value of being in every single state. These states can be I'll show you a good example later. So one there is something called Bellman equation. Actually, in deep Q learning, we use this Bellman equation. So I think it's good time to pay attention to. So if you've been doing math, this is going to be really straightforward for you. So this g of t is you expect is it can be defined as what is g of t. You can see this, right? Can be defined like that until infinity for the current state. So this g of t can be described with this. So just take this gamma out, and then you'll get g of t plus 2 until everything. So what that means is the goal of the next state. So g of t plus 1, that's the goal of the next state. And what's the goal of the next state from here? As you can see, that's the value of the next state. So the value of being in a state is the sum of rewards obtained in the next state, and then the discounted value of being in next state. That can be like a value function for being in a current state. Why this matters is this term in here. This is going to refer. This is going to take you forward. So this determines whether you're going to reach the goal or not, and this one is like what is the immediate reward you get. That also matters. Right? So now we are moving on to Markov decision processes. So it can be represented as a tuple of state, action, probability, transition probability, and then reward, and then discount factor. So these things we have covered. So we have covered state, action, probability matrix, and the reward and discount factor. Now let's try to understand a policy. What policy means is behavior of the agent. That's literally what it means. In a way that you can change this policy in a way that you reach the goal. That it's a way of saying how you behave in an environment. If you can behave in a specific way, then you can reach the goal. That's the thing we're trying to find out. There might be several policies, but now we're just defining what one policy is. Okay. Policy is represented in pi for a state action pair. The policy might be state action pair. It's probability of this is talking about from taking from all states and all actions. So now we can break this down into two. Now that we have defined the what policy is, now we can understand what is the value for being in a state and what is the value for taking an action. Taking an action is dependent on the state. That's why you have S down there. So value is represented as v of pi of s means value of being in a state is the expectation of uh, expectation that you reach the goal given that you're in a current state by following a policy. That's what this function means. And q pi means, q is like can be described as quality value. They're pretty similar, right? In terms of words, that I think that's why they've used these. uh, Here we include another term called action. Here we also consider in every state what action we do, and if that takes us to the goal or not. That's just one extra term. So here also the Bellman equation can be used to simplify this thing. So, you know, we have seen how Bellman equation can be used before. So it was in a similar form. So we can break this down as well. We're going to break this one this actually. Uh, this is a Bellman equation. After converting this into Bellman equation form, then we can do uh, QLearning, deep learning, everything. So now that we have talked about value of being in a state, now we are talking now policy of being in a state. We have talked about value. We have talked about rewards, and now what's the optimal state value function? What is the optimal uh, op, you're getting the point, right? What is this optimum of choosing these things? What's the best of all policies? So if you find the best of all policies, game over. RL is solve the environment, completely. There is no better solution than this. That's exactly what it means. uh, the maximum of all values possible for given a state for all states. So if we know that, that's it. Uh, we know how to get to the best states right away in order to achieve the goal, right? So yeah, we should also keep that in mind. So the action value pair is maximum value for all actions. You could take maximum reward that you would get for taking an action in every single state for all states. If you know that, again, you solve the environment. We are trying to we cannot find this exactly, but we would try to, in using these q learning and deep q learning algorithms, we would try to go near these q values. This is important. This is why there is something called q learning. We are going to learn this. We're going to learn this optimal action value fast. And after applying the Bellman equation, this it becomes in this form: the immediate reward and the discounted optimal q values from the next state. So this introduces a bit of problem for deep neural networks. We'll see that later. So finally, we are into q learning. Okay, 42 minutes on. I think I'm going a bit slow. So let me speed this up. Q learning, yeah, it means essentially learning this optimal Q value. So at least trying to learn what these optimal Q values. And there are several ways of achieving this. One such way is an iterative solution of trying to be in every single statement and try to take every single action so that we can take the maximum of every single state action pair. So that's one solution. That's actually called iterative solution. So this is exactly what q learning really is. So let's say let me show the next slide. Okay, so I've an example for you. Let's say this is an environment where there are 9 places your dog can be. Your dog is the agent, and the goal of the dog is to reach here, right? Is to reach this. When it reaches here, the episode is done, and then it could restart again. So first, let's say your dog is here. Uh, if it moves here, this is a pit. This is one of the worst depictions of pit that you can see. If your dog would fall away and say this, that's the idea. So let's say your dog chooses some actions at the start, and then you know. Uh, if we don't know these q values, right? We are trying to try to find these q values for being in every single state. That is what that matters, because we don't know anything at the start. We have to start from scratch, knowing nothing. So there are three possibilities of this dog being in the next stage. This is the current state. The dog can move here, can move here, can move here. So if it moves here, it gets -1 of reward. For instance, move to empty box gives -1, -1, and if it moves here, it will get a large negative reward. Okay, so if it moves two steps, let's say we are in st+2 and it moves here, it gets a reward of +1. Now that we know we are getting a reward here, the value of this is going to shoot up in our Q table. Using the algorithms using the equation that we have seen before, we can calculate these values for every state action pair, and some state action pair can take you here, that's for sure. But also the states are finite, right? So also state action, everything is finite. uh, when you get here, and then when you keep computing the max q values of what is already known, that would become a problem, because uh, also the next time it will go here every single time, so it would never reach an end. This happens. This is called exploitation exploration trade-off. Here your agent is trying to try to exploit the environment. So if it had more moved here, and also this is two steps, right? This is also two steps. If your agent is clever enough to explore here, then taking one step would be game over. So if you the idea here is your agent has to explore at the same level as how much it is going to exploit. There has to be a right balance in between exploration and exploitation, so that we can actually try to get to the best goal. Okay, I hope that made sense. So that's this thing, epsilon greedy strategy. What that means is, sometimes we take random actions and sometimes we take greedy action. Greedy action means exploiting the environment. Okay, so let's move on. Yeah, I think I've explained everything here. Yeah, I've missed one. So there's something called a Q table. We saw transition probability, right? Likewise, we have a table that represents uh, q values for every single state action pair. So if we move in here, we can estimate the q maximum possible q value for being in a state at time. When our agents is starting to learn based on exploration or exploitation, might have learned better, and then they might have several values for which you might choose the maximum value here, maximum value. So you store these values in form of table. So here it would be like there are nine actions and four actions and nine possible states. It might be like 9 times 4. So this is very small. This is one of the most uh, simplest environment to think of. Let's say you're trying to solve something else, like I'll talk about that later actually. What happens when you have a large state action space? Here's the, here the state space is very small. That's why we're we're getting away with just building a Q table. So this, I think I've talked about this exploration and exploitation trade-off. So when we should also try to go in the right direction, but there should be a sanity check that we explored enough that we are going so that we can compare multiple actions and decide which is the right one. Okay, so this there is one example I can say. Let's say you're doing a trade agent or something like that. Choose doing an it figures out that doing an action can give a reward. It could be any action, could be as complicated as it can be, and learns this reward. If you don't explore enough, you wouldn't explore any other way of that could even take you to an even greater reward. So also it could lead to a catastrophic negative reward. So that's why it's called trial and error learning. This unit reinforcement learning, by the way. So let's move on to deep Q learning. Now that we know what Q values are, now that we know what Q learning is, we're trying to solve the problem at hand. This is really the thing, the topic of the discussion today. Deep Q learning. So Q tables are good enough for small small state space and action spaces. But what happens when your state space is huge? One way of thinking about this is there is a popular video game called Dota 2. So if there are some gamers out here, you might straight away understand what is Dota 2. Dota 2 is a famous video game. I'm explaining to others. So in this is an open world game. So it could be any game that you imagine. Building this type of tables for every single state action pair is going to be extremely inefficient. This is computationally infeasible to handle. So this was a problem for a long time. I think until 2013, where deep networks really rose in fame, and then like everyone, DeepMind, OpenAI, and they just democratized this thing uh, by making a lot of environments open source. So the idea here is we were trying to use the Q table as an approximator to choose the next action there. So the Q table is your approximator in Q learning. So in deep Q learning, you're just going to throw away that the table aside and then bring in a deep neural network. Why a deep neural network? Deep networks are good at identifying patterns. We might not have to store huge amounts of data. All right. So if this is a big video game, we might need terabytes of storage to store all the state action value pairs. But reinforcement takes time. This could be fast. Q learning could be slow. So let's move on to the
Hello, Abhi. Abhi, are you there?
yeah, can you hear me?
Yeah, it's clear now. Yeah, go ahead.
Yeah, I think there's an internet glitch. 1 minute.
Okay, fine. Yeah, hi. We will move on to the code part in a bit. So we will actually implement the Q learning algorithm in TensorFlow, and we will see how things work. So yeah, Abhi, is your mic fixed? Hey guys, yeah, stay with us. 2 more minutes, you'll just rejoin. Okay. So meanwhile, you can ask your questions in the Slido link which we have shared. I've just dropped the link and the ID in the chat box. Right. You can ask your questions. It might be specific to reinforcement learning, or else for the today's session, or else it might be a question in general to how to get started with reinforcement learning and what are the tools and available. So as far as I know, like if you're uh, passionate about, like if you wanted to like actually work with reinforcement algorithms, it is not like traditional supervised learning or unsupervised learning. So those follow a different method. So here, if you're keen in robotics or else self-driving cars or else learning from environment, so that is where reinforcement learning and q learning is one of the oldest technique, and it's been used, but after deep learning revolution, deep q learning, it has been rebranded or reframed as deep q learning. It's more used in most of the places, even if you see OpenAI gym. So all the algorithms, let's say motor control or like walking from scratch, a robot walking from scratch in a 3D environment, or else landing a drone, or else a car navigating through a route. So everything is about learning from the environment. So they make mistakes over and over and again, and actually they learn from the environment. Yeah. So yeah, Abhi is still trying to fix it. 1 second, give me a minute. Yeah. Yeah, I think you should be able to see my screen. So just scroll down to the slides.
Yeah, can you hear me?
Yeah, Abhi, it's clear now. Yeah, go ahead. Abhi, you can continue.
Okay, so sorry for the delay. Actually, I had a brief power cut that's caused internet to go off. If internet is not available, then in laptop, my mobile internet isn't good enough to handle this. So that's why I asked Navneet to share.
Okay, Abhi, yeah, I will switch the slides. You can start explaining.
That now can be approximated with a deep neural network. So that's the idea. So what this diagram down below is depicting is for every state, the the q the this deep neural network algorithm will output the value of b a value of taking in action. So if you're trying to move in a room, like, there might be several state inputs, but there can only be a finite set of actions that you can take in any environment, mostly. So moving forward, backward, right, left, if that is your action, then there's going to be four output nodes at the end. So that which is trying to estimate the best possible action that you can take from given in every state. Given a state, best action you can take. Bro, just hit control L. Okay. Okay, I think My connection is back. I'll try to log in a couple of minutes.
Okay.
So this brings us on to another concept called experience replay. So why do we need this? This traces back to the previous. That's why I've introduced you to some of the bare minimums that you should be able to understand in the RL. So can you go back to the Bellman equation slide, please? Yeah, after this, next one, the final, next. Sorry, actually, I told you to go forward.
Forward. Fine. This one.
So this is it. This is it. Yeah.
Okay.
So by applying the Bellman equation, we can solve the optimal Q values. So this is an approximation right now. Thus we're going to solve this for every single state action pair. So what this essentially means is the maximum value of being in a state and taking an action is the expectation of the next reward plus the discounted sum of the maximum value that can be obtained from the next state. So the thing is the max term on the right hand side is going to cause a lot of problems because we can easily estimate the current what action to take now. If that action uh, it can give you the R of t plus one, but it cannot give you the maximum that can be obtained from the next state. So that's a problem, So that we'll see how to handle that later. So now we're going to introduce a concept called replay memory and see why replay memory is useful, and then move on to this thing. Okay, okay, can go to replay memory slide now. Okay, I'm trying to share my own screen. Uh, some seconds, please. So I think you have to allow me to share screen.
Yeah, be 1 second.
Okay.
Okay, you can share your screen now.
Okay, you can see, right?
Yeah, it's clear.
So we're here. So experience replay. So neural networks cannot have, when you take an action and this happens in a consequence, in a sequence, or when you take sequence of actions and that takes you to sequence of states, and that's going to be if you uh, the point that I'm trying to make is this this unpredictability is going to trouble your neural network. So and also we have to break the correlation between these the dependence between one time step and the next. If it is so, then it is possible that your neural network can learn specific set of following a specific state, following specific states or something like that, and might pick that up more than the rest. So that's the reason why we need replay memory. Replay memory can be defined. It's like it's like a data. It's like the data that we're going to sample from, just like normal deep learning. We're going to sample from this replay memory instead of uh, taking actions and that randomness having more say than anything else on a neural network. That we don't want that to happen, right? So that's why we have this. Initially, we define a specific size. uh, until we hit that, we take actions based on explore epsilon greedy strategy. And after you reach a stage where you have enough to go into replay memory, then you have already stored these things. So then this training starts. What happens is you randomly sample a mini batch of sequences, or sometimes even a batch of sequences, or sometimes even a single sample. You randomly sample in this example, let's say you just randomly sample a bunch of samples from your replay memory. So now until that point, your replay memory will get filled, until the minimum threshold is something you define. So until it hits it, your agent will keep doing things. So this is actually deceiving when actually training a deep tree network, because you will see that the training is fast. If you're using something like TQDM, it will say your training is going to complete very soon. But that's because you haven't hit your replay memory yet, and you haven't really started training. So that has deceived me. So in terms of the code I write, that happens, might not in someone else's code. So there is no, I don't think there is any framework to do deep learning and stuff like that as of now. So why this needed is we should also break the correlation between successive samples, which could introduce an unnecessary bias. This solves two problems. We're using this replay memory, which helps our neural network. And also we are breaking the correlation between successive samples, which could introduce an unnecessary bias in the network. So this E of t is the experience. Let's say you're in a state S of t, and then you take some action, you get a reward, and you transition to state S of t plus 1. So this is the state that you're in, S of t, and then this is the action you took, A of t, and then this is the reward that you're going to get, you got for taking this action. So that reward is going to transition to the next state, and then you get the reward. And then it's like this can be treated like an experience of what has happened from for taking an action in a state. So this what this means is we should also be able to remember certain things about the past that we've taken, so that we don't keep doing the same mistake. uh, I think that's the whole point. This is all inspired from the way real real world organisms and even humans, how they behave. So sometimes it might be like the science of decision making. In a way it is, in a way this is science of decision making. So target network. So this is what I was talking about when we were talking about the max term and Bellman equation. Let's go there actually. So the best possible value that you can give, given that you're in a state and you take an action A, is the expectation of the next reward and the discounted maximum value that you can obtain in the next state. So this discounted maximum reward that you can obtain in the next state is unknown. You can do this as we have seen in this network, like choose the best action here, take a max out of it. You get a maximum, which leads you to the maximum reward. You can get out this, but you cannot do this. And if you do also, it is possible, without a target network you can train a DQ network. But in DQ learning you can or cannot use these target networks. But using networks actually almost always works fine. So we'll stick on to using target network because if we don't, then we are significantly cutting off one single portion of deep Q learning strategy. So we should include that. Okay. So what the target network means is we're going to use a separate network to calculate this max Qs for the next state. That's exactly what it means. So you know if you can see this, this is actually a good definition actually. If S and S prime have only one step in between and they share the same network, chances are optimizer updates Q values along with target Qs as well. This what this means is uh, you you estimate the value of the current state, and by using the reward that you get and then the reward that you get in the future. If you try to do that in the same function, like fit operations in machine learning, two fit operations in the same network, then you might miss the parameters up. Okay. So uh, also along with your obviously your current your q values will move towards the optimal q values, but the problem with that is your optimal q values would also move away from you. So it's not a supervised learning problem where your optimal q value is fixed. Your optimal q value also has to be learned. So your current q values have should reach try to reach the optimal q values, but the catch here is the optimal q values will also try to move away from. So it would be like somebody chasing their own shadow or something, an animal trying to chase their own tail. It's something like that. uh, and this makes the neural network very unstable. In some cases, very simple environments, this can work actually. We are going to solve the lunar lander problem here, where we try to land a spacecraft in a simulated environment. I've experimented with both with and without target networks. There has been a significant increase in performance with target networks, but you can also solve the problem without target networks. If just solving the environment is your problem, then target networks may or may not help. So this is the uh, algorithm of deep Q learning. All right, this is a little bit huge. When I'm trying to explain things with the code, I think you will understand it better, because every time that happens, right, when you see something like this, an algorithm, and you just instantly freak out, but when you see the code, it makes a whole lot of sense to you. So first thing that you want, or that you're doing in a deep Q learning algorithm, is to initialize the replay capacity. Okay, so the next thing you do is initialize the policy network with random ways. That is something we do in deep learning as well. Random initialization. Okay, so we do random initialization for neural networks all the time. So that's exactly what we do. Just that we are calling one network as a policy network, another as target. Because first we random initialize our main network, that's called policy network, and then we clone the policy network. How do we clone? We just use the same architecture, initialize it in the same way as we have initialized the policy network. So that would give us two identical models to start with. So what happens is, what is an episode? I think I didn't explain the concept of episodes here yet. So if we take the example of playing a chess game, then playing the game once is an episode. Or you're trying to land a spacecraft in lunar surface, then trying to land one time is an episode. It's like that. So if you're trying to play a game like Pong, then Pong is like it will be like table tennis, like two blocks here moving around at either end of the screen and a ball bouncing over. These one might be the CPU control player, another might be the human control player, and you'll get scores depending upon you miss or you make the opponent miss. So doing this like one set of after one set is over, it can be treated like an episode. I think now you can get the idea of what an episode is. First we should initialize the starting state. Initializing the starting state is the environment takes care of this. Actually, in OpenAI environment, really, let's say if this is the area where you try to land, if you get initialized in here, that's not a really good thing. It would be easier for you. You might be initialized somewhere here ideally. If you're trying to land on the moon in real life, you don't instantly go near the surface. That's what I really mean. So we should initialize the starting state in a meaningful way. This also matters, but when we're using OpenAI Gym and things like that, it will take care of that step. We don't have to deal with that. So there we have to reset the environment. Okay, so after an episode is finished, we should reset the environment. So for each time step inside an environment, now you're inside an environment. Let's say your bot is somewhere, spacecraft is somewhere in here. Then each time step would be the state action pass that you're going to do, trying to land this right in here. There can be several time steps that go in a single episode. Uh, Execute select first. You randomly select an action and start with, so there is no meaning in starting after starting stage. Then the rest of the thing is going to make sense. We have covered most of this, and observe the reward, and we go to the next step. Take an action. You get the reward, and then you transition to the next state, and then you store these thing in the replay memory until you hit that minimum threshold that you've actually defined previously. So until you hit that, actually you have to keep doing this. I didn't add that. Okay, so random, and then after reaching that, when that becomes true, then we will hit into training, and where we'll sample a random batch from a replay memory. Now we have saved many state action, what happened in every state. That's exactly what we have saved. Not just what happened, we have saved which state we're in, which action we took, how much reward we got, and then which state did we transition to. You save everything in a replay memory for that specific state action. All right. So it's just like since we randomly sample, that doesn't matter which state you are in. Right? It can all be stored in a single tuple of the things I mentioned, and pre-process state from batch. So okay, this is not needed for us now, but for solving the lunar lander. But we might need this when we are trying to solve Dota 2, for example, where our inputs might be in form of pixels. Without pixels, how do you understand where you are in an open world environment? Here, you can save with the positive rewards that if you're going towards the target or not. All right, so it is not possible there. So we just pass into a policy network, pass the entire batch that we have sampled out from a replay memory, and then calculate the output Q values and target Q values. The output Q values can be calculated like this, as I shown before. It's very simple. Uh, the target Q values requires us to use the target network, which we use to, uh, you know, determine the value that we would get in the next year that we're going to transition to is estimated by a target. Okay, let me repeat that. So, given that you're taking an action, then it would take you to another state. So the value of being in the next state is going to be determined by your target network, but the current state is going to be determined by your normal policy network. So these might be, there has to be some fixed steps here. For example, after which we update the target network with the policy network's weights. That way we don't uh, we this reduces the imbalance. At least our q values can remain the same. It's not going to mess up with the neural network parameters when you do two fits. So the first thing you might notice here is this is a lot of fits. Fit operations is like this fitting a model to a data. So in machine learning, so there's going to be a lot of fits for each single episode. There are going to be several episodes here. So this is going to take a lot of time to train, depending upon how big a model you use and how big your state action spaces are. Okay, so before moving on to the actual solution of this lunar lander, we just formally describe what this is. This is the spaceship I was talking about. Yeah, either it can fire its main engine or its side engines, and it can go to different states, or it can also do nothing. That's why there is a value called do nothing. When we reach here, we shouldn't do anything. That's explicit. We we shouldn't do anything. Otherwise, we are never going to reach the goal stage. We fly over again and then we fail. So there has to be some action like this in environments of this sort. So this is going to be a long thing. It's not going to be this short. So it is going to be a little bit of harder problem for us to solve, because this is not an easy problem to solve for our first environment. That's why we're using deep Q networks here. So I wanted to take something where it's not so easy for a deep Q network, but it's also not too hard for a deep Q network. So it has the right balance between that. So that's why I chose this. Is also one of the most exciting uh, problems that I have found out. This could be a robot. If you have a robot like or a spacecraft like this, depending upon what you perceive from the environment, this can be completely translated to the real world. Problem with that is, yeah, sometimes if your spacecraft crashes, then that's a big problem. But in a simulated environment, it is not. If you want to see the code or play around with the code, you can go to YouTube, this GitHub link. Now let me open up the code and just walk you through. Meanwhile, let's also explore the GitHub repo actually. You can go through this, read me stuff. This is not really a great explanation of how things happen, but uh, you can Google always if something goes wrong. So in the source folder, we have all the code that we need. Models, we have the trained models, the models that I trained, and results, obviously the results, and slides, the slides. So these two files, this requirements.txt file is everything you need to install to make this work. Just do it like you know, yeah. If you do this, you can try to install everything, but it might cause some problem depending upon what configuration you have. So I suggest you to go ahead and install each of these in separately. For example, like TensorFlow can cause you a lot of problems even in a virtual environment. So I went through this, and first let's open up the DQ. Okay. So is the code clear? Yeah, I hope it is visible. So let's get started now. So the first inside SRC folder, I have several of these Python files. This is custom TensorFlow. I think you can or you can throw it away. This doesn't matter. But these three are the most important files. It's just for TensorBoard. Since we are TensorBoard, it updates on every single fit that you make in TensorFlow. But we don't want to do that. We have to update the TensorBoard only after a single episode. So that's why I wrote a separate script for that to update that only after an episode, not after every fit. So let's get into the DQ and script first. So uh, this is like common imports that I've made in every single file. So I think that I have to clean. There is a lot to clean the imports here. So nonetheless, so let's start off from here. So first, I'm defining a deep network class. So what I'm literally trying to do is just create this model with layer one size. We have two layers here, so two fully connected layers. There is no convolution layers here. Uh, there is no extra pre-processing steps that we need. So you can add convolutional layers for this problem too. This convolutional layers, where this can be used is something like this. I've showed you before. You can have a convolutional layer, especially when your environment is very visual. So in here you have to know where the ball is going. Otherwise, you cannot just take random. You cannot be blind here. So that's why we need to pass inputs as images in this kind of RL problems. So in here we don't need. I'm just trying to land in a separate area. So we're under gravity. We know where we're going. As long as we can correctly estimate the reward, we can go to the right direction. And you know, this could be like this cannot be just one frame. It could be a sequence of frames for every single state. So it would be very hard for the neural network to estimate if there is only a single frame from which for it is asked to make a decision. Uh, in contrast to a set of. So depending upon that, your architecture can vary. So I'm just going with the simplest of approaches that I can here. And this is, if you already don't know TensorFlow, okay, this is just TensorFlow Keras, TF2 symbol Keras model. I can show you the versions. If you, the version is 2.1. I know. This should give you TensorFlow 2.1. That's batting later. So we have a lot to cover, which is very short time. Uh, so we're just defining the input dimension. This input dimension is going to be like the observation space size or something like that, and the actions is like the actions that you're going to take. The activation function here can be relu, but in the final layer it should be linear. It is treated almost like a regression problem. Like if you have four actions, right, as I mentioned before, firing the main engine, left, right, and the doing nothing is 0, and firing the main engine is 1, left, right is 3 and 4. So in that way, to represent each action, we just represent form of numbers. So we need linear activation function at the end. I'm using mean squared error as loss function here. Plotting the loss cannot be useful in RL, because all we care about is the cumulative sum of rewards that we're trying to optimize. If that increases, the if the minimum reward for each episode is trying like follows an increasing curve, then that's good. So I'm just defining a neural network here in form of a class which we are going to utilize from the agent. So this one way I just try to operate it, because I name everything beforehand. I name hyperparameters and things that are like having a big say on the model in caps. You can do anything, you know. So we need NumPy obviously. We have imported Gym, TensorFlow. We imported the deep key network and the TensorBoard that we have defined here and here. So we need a replay memory. As I said, this can be many people use double-ended queues for this. That's why I've imported the DQ. DQDM is just a progress bar OS. Time is also a Python module. Random, everything is Python module. So uh, I'm just suppressing few errors because this doesn't have a GPU, and I have some installation errors that pop up. So I'm just suppressing them. There's not errors, just warnings. Sorry. So at the first section, we are going to define whatever we need in order to create this agent, and then we at the second stage is creating the agent, and then third state is section is using the agent. Okay, so we have defined the model name. That's just as a matter of convenience. We are having a discount factor of 0.99. As we now that you understand discount factor, I think this reduces a lot of your. If you understood this discount factor is fine. If you don't, it's going to be a problem. That's why I just at least had to touch over these concepts, because this algorithm is completely different from any machine learning models that you might see. So uh, it is important to understand every single, at least the abstract overview of all the nuances you need to create this algorithm. So minimum replay memory size is something I told. If until this hits, we keep taking actions based on epsilon greedy strategy, and until that point we don't train. That's also important. And then the replay memory size. Uh, and even use a double-ended queue, things can come in and go out in another way. So uh, if what this means is, we're just keeping the last 50k experiences. This could be even a larger number. This could be, I have seen people use like a huge replay memories. uh, the mini batch size is 64. This the size of the sample. This is the 64 samples that we'll sample out from our replay memory every time. That's the mini batch size. So update target every is 5. This I told you, this is also another hyperparameter that we can tune when to update the target network. So we've defined this as 5. For every 5 episodes we just update the network. And minimum reward, for just for the sake of saving the model, we're just starting off with -100. So memory fraction and learning rate. Learning rate, I think learning rate must be very clear to you. This is like the learning rate also comes in RL. So that's one, at least one common thing that you can relate with the general machine learning paradigm. So that's RL. Mm, okay, we have imported Gym, and we are making the lunar lander, and we are defining the episodes to be 100, run for 1,000 episodes. That's not a huge number, but training for 1,000 episodes, that took me about 2 hours in a decent AWS instance, right? So it took about 2 hours. So obviously we cannot train that now. We don't have the time to train this. So input dimension is the observation shape. So as I said, so the number of actions is the number of actions that you can take. So first layer I'm using 512 units, and second layer we're using 256 units. So these values straightly go in here. So I designed these in this way because I don't have to change a lot of things. That's where object-oriented programming comes in. Right? So just trying to make use of whatever in order to reduce the development time. And to say this is very important when you're competing in Kaggle competition and stuff like that. You need to do a lot of things, and you are competing with people, and the time frame of 3 months might be a lot less than you think. And Aggregate stats every is updating the stats for every single episode, or you know things like that. For this, for the TensorFlow. Uh, okay, so preview is false. That's because we are not going to render while training. Render, what it does is it shows up this screen of what is happening. So render is slow. Generally, render is always slow. So we just don't do that while training. You can try to do that. Absolutely no problem with that. But just that it will be slow. I just setting the random seeds here to ensure there is at least some degree of reproducibility, and then uh, this logs folder and results folder, there is no, sorry, logs and models folder. Initially they were not, so I just created in here. So the DQN agent, first we are initializing the DQN agent with whatever uh, you know things that we have defined above, like the model name, input dimension, actions, layer one size, learning rate, things like that. And then we can use the create model. This is just for initializing. All this does is here. All right. So nothing happens. There is no model created here. When we call this method here, a model gets generated and we get that back. So we're going to initialize that for the current class. That's TQN for the agent. The agent's model is this. Then we are saying the target model. Just create one target model. The good thing with TensorFlow and Keras, PyTorch, and everything, it takes care of the initialization stages. It takes care of many other things as well. Just that we have introduced that thing in our algorithm. This is taken care of TensorFlow for us. So target model dot set weights is this model. Self dot model refers to here. This dot get weights. So self dot model dot get weights. So the target model's weight. What I'm trying to do here is to make the target model's weights same as the uh, policy network weights. So just initializing the replay memory. Okay, replay memory as a max length that we have defined before. And, according to that, it gets uh, just have to specify the log dir and the format that you want to save the the files for the tensor board, so that you can render them up later. So target update counter is just the counter. Every 5 times we need to update this, right? So we need at least some kind of a counter that keeps track of what is the current situation and when do I have to update. So we need this counter for that. So we need to update replay memory as well. So we need to definitely update replay memory instead of taking care of that as like given in an algorithm. We just simplify it by defining a lot of functions, sorry, methods. So self dot replay memory, the up and up transition. This transition can be like the current state, the action you took, the reward you got, and then which state you transition to. This is a tuple of all the information I just said. So Q values, we just want to maximize whatever the network has learned. So what is the best Q values the network has learned? Please give that. So this code just gives that. There might be certain things in here which you don't understand, but as you start experimenting with this and like start to uh, really understand what is happening behind every single line by executing this, you'll definitely get right. So if the replay, then we define the training method, where if we don't want to train, right? We don't want to train if our replay memory size is very small. In this case, if our replay memory size is less than 1,000, we don't even have to train. So that's why I'm just outright blank returning with nothing. So you might include some other thing like if else statements, and then just check what is the size of minimum replay size, and sorry, what is the size of your replay memory, and then do that as well. That's fine, completely fine. So it's just one way of doing this. Everything in here might be just one way of doing this, but it accomplishes our goal. So as long as it accomplishes our goal, uh, it's not bad. So now we're going to sample out the mini batch from the replay memory. Provided that we are passing this step, we will come down here, and then self-dot replay memory is the actual replay memory, and then the batch size. The random dot sample sum. according to this batches. For example, we have 500. If we have a list with 500 numbers, then if your mini batch size is 100, then it will sample out 100 numbers completely random. In this case, it's just that it's from replay memory. So the current states, you need to get the current states first. You need to uh, go over these mini batch and current state. As I said, wait, let me show you the tuple. Otherwise, it will not make sense. So current state, action, reward, next state. Now, whether it is done is also whether we have reached the goal is also part of this. So I might have missed that before. So zero means current state. I'm trying to access the zeroth element from the tuple. Okay, where is that? Okay. Yeah, we're trying to access the zeroth element on the transition, and that is just the current state that we were in. So this is all the replay memory. So it is in the past. So we just sample out, they train them. So the idea behind this is, whatever you action that you've taken before, you just trying to optimize this action in a way that can lead you towards the goal. So that's why we're sampling out the current state, and then current queues list is like a self dot model dot predict on current state. This is this forward prop in the model. This forward prop that I told you that we would do. This is this forward prop, right? So sorry, this is just a predict function. This forward prop comes later. So this the next current states can also be got from the tuple that I mentioned. This is just the fourth element, so we're using three. So future queues list is going to be predicted by the future target network. So we're just using this predict function in that network. We haven't yet trained yet. So that is something to note. Uh, the idea here is, as I said, we take some actions and then we see how good the actions are, and then and then update the weights so that we can get towards our goal. So just first we have to estimate the current queues and future queues in order to get what is the value of being in that state. That's the Bellman equation that we were talking about. So we have just obtained this from the neural network. So I'm just enumerating over the mini batch. So this is the mini batch, like returns this we have talked about. So I also need the index. So I just pulled away the index. That's why I'm using an enumerate. And if it is not done, so if you're in an episode, if you're in an episode is not done, and then just get the future max queue, and then the new queue might be the reward and the discount plus whatever best action that you take from this step. So if you're finished, then it's just going to be the reward. There's going to be new queue value after you reach the terminal state. So that's called the end state or goal state or something like that. To denote that, I've used this. Okay, so we just update our queue values now. Remember, we have to update our current queue sequence memory and everything like that, and that way we can travel towards the direction that takes us towards the goal. So this is just for the neural networks purposes. I'm using X and Y. This get reinitialized in every single step, train step, and then now that we know what happens, we just can pass this in a model.fit, and then this callback thing is we're calling the tensor board. You know, if we didn't yet reach the uh, terminal state, we are not going to update the tensor. This tensor board is for keeping track of what has happened. We just care about what happened in the episode after the episode, not during the episode. Yeah, it could be like what the outcome of the episode is what we care about, not how that outcome happened. In the end, we need to improve the outcome of the episodes. Okay, just updating the target counter. If we reach the target counter, just get it on and update it. All right, this is everything about defining DQ and agent. So now we are just going to use it. Right. So I'm just initializing the DQ and agent here, and right, which is going over all the episodes that were defined, and then first we are going to take a step of TensorBoard step. You can throw this away. You can keep this or throw this away. I'll pull up the TensorBoard and show you what will happen at the end. Um, at the start of every episode, there has to be there has it should be zero and then it could be updated. The past values can be tracked, but every single time just we refresh the episode reward for every single episode. For every single episode, you can take several actions. So there's steps. Yeah, sometimes like when your agent will keep taking actions, and then there has to be some number of steps after which you decide that your agent has already failed. So it could be that your uh, your spacecraft is trying to land, but it never lands, and keep trying for a long time. We don't have to wait for several hours for this to land. It should take some time. That's optimal. So done equal to false initially. So while not done, this is the epsilon greedy that I was talking about. This is random dot. This gives a value in between 0 and 1, or the epsilon is I think 0.99 here. Or 1% of the times we just go about it like maximum q value, and then yeah, get best possible, like exploring and exploiting. So otherwise you take randomly pick one of these actions. Otherwise you get the q values, what the best greedy action take. So this is specific to OpenAI Gym. So we're stepping through the environment, and then this gives back new state reward, and this log. This describes some debug information as well. So we don't need that. So I'm just ignoring it with the underscore. Update the episode reward. So what is the sum of the reward that we got after the episode is what we care about. That's cumulative sum of rewards. And then we update the replay memory using the functions that we have written, and then we train. Yeah, that's about it. Like, then you transition to next state. So current state equal to next state. Just if you go over this script, you can better understand than just understanding it in one go. So for this is specific to TensorBoard. I'm just calculating the minimum maximum reward for an episode, average reward, and then updating it. So we save the model as soon as our algorithm hits desired minimum reward. You could save this for all episodes, or you could save it after the end of all episodes. It depends on you. So we should also decay this epsilon rate. That's why I'm just multiplying by the epsilon decay rate. This is the epsilon decay rate that we have defined previously. So we also have a min epsilon in place. So if we keep decaying this value, it will go down. So after there is no point in decaying after minimum epsilon. Yeah, we have to retain that minimum value that we have set. So that's why I use max of min epsilon. Min epsilon and epsilon. This is a lot. Actually, this is almost what 200 lines of code. Yeah, 250 almost. So after this training process completes, we get a saved model. So I have several lunar lander experiments. So that's why you would have seen a lot of them. So you go to results. That's just a result of making inference. So first, let's look at these models that we have saved. So as I said, uh, there's only two episodes where we hit that minimum reward we set. So when that hits it, it saves the model. It saves the entire model in here. This is based on Keras's save model, load model functions. Okay, let's quickly go through this inference script as well. I know we're running out of time, and this is essentially the same, but I'm just throwing away the tensor board here to make during inference. We don't need any log. We don't need to keep track of anything. Just need to see the results. So and I've just added a simple step in here, like if load model is not known, just load model. Otherwise, create a new model. That should be. I think that should make sense. So that these are the two changes and no TensorBoard stuff here. I think that's about it. It's the fastest way of making infrastructure. It's not the best way, of course. So let's look at some of these results. All right. So this is somewhere in the later stages of training. So it's one model. This happens. So it makes a wrong decision, and then that leads it to it failing. But it is trying to do something. You wouldn't. The results are nowhere near this good when you start. Yeah, I'll show you something. You see that? This also happens. There's a lot of it. This will happen at the early stages. This is also one set of results after running the inference script. That is it. We have done reinforcement learning. Look at that. It is landing successfully on almost all the time. Sometimes it might fail. It's not perfect like this. Yeah. I think we're done here with the code. Yeah, I'll show you the TensorFlow.
Yeah, I think we are already 20 minutes past. So you can just show the tensor board, and we will take up some questions, and we will end the session for now. Yeah.
Okay, fine.
Okay. Fine. Sir, there's a spelling mistake.
I think we can end. It's not showing up.
Yeah, it's okay. Yeah, like I think it's not as easy as traditional supervised learning or regression or CNN or whatever it is. It's like a lot of math involved and a lot of different perspective on the problem statement, or different thinking is needed to work with reinforcement learning. I think, yeah.
Yeah.
So yeah, like meanwhile, you can share some of the resources to get started with reinforcement learning with a background as a beginner, or else with a background from deep learning or machine learning. And
Yeah.
they have few questions asked in the Slido, so we can try to answer some 2 or 3 questions, and we will inform now, right? Okay.
Okay.
Yeah, like you can just share the resources. Meanwhile, I will send you the Slido link. Yeah, Abhi. Okay, yeah, you can just explain 1 or 2 courses. Rest of the things we can compile it into an GitHub page, and we will share it to all the participants, right?
Yeah. Okay. So I think the first resource I would recommend, if you want to go into the mathematical aspects and understand the concepts, it is definitely David Silver's lectures. This guy David Silver is like the guru of RL, not like Andrew Ng, not at that level, but he's a very influential guy in this field. So these are very crystal clear explanations of this of oral concepts. You know, I don't think it could get any better. It could be, but I just love. Many people love these lectures, this lecture series, and he also gives all the materials out for free. And then you can try this book uh, on it. So this book by Reinforcement Learning and Introduction by Andrew Barton and Richard Souton, and that's also an excellent book. This is like the you know. Hello.
Yeah, Abhi, yeah, you're on. Go ahead.
Okay, again there is an interruption.
Fine, 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 no issues.
Okay, so oh, how is it still displaying? Okay, so this Richard Souton and Andrew Barton book is good. It's like the very important book of RL right now. And then the deep reinforcement learning book by Maxime Lapin is good. So that's something I so So good. So as I said, there are not of great there are not a lot. He talks about actual practical aspects of deep learning. I'm just in earlier phases still. There are
Okay,
like
yeah, like
a
your
lot
voice
of
is not
GitHub
that clear.
repos
I
for
think
you
there
to
are
learn from.
few.
There are a lot. Just Google and get. Just by googling, you can learn a lot.
Hello, Abhi, are you there? Okay. Yeah, like yeah, I think like there are a few more participants. Sorry for the inconvenience happened today. Like there were like few electric glitches and internet problem, no issues. I think we will compile down all the resources into one email or else in one GitHub page, and I will share it, post it on the Meetup comment section so that you can access it. And the questions that you have posted on the Slido, we will try to answer those questions in our forum, or else we will compile it again with the same GitHub page, right? Like Abhi, are you still there?
Yeah, I'm.
Okay, so yeah, so you can just give an end note and we will end the session, right?
Yeah.
Okay.
So you would have, if you went through the whole thing, and you would be like, there is a lot to understand in RL just to get to solve a simple environment. So that's it. Uh, we are in a stage where there are not good resources, and the field is still developing, and it might get to a might get to become something like deep learning in the future. Because if there are a lot of possibilities. There is neural architecture search using RL that's going on. So that's very interesting, because if you could uh, use RL to find the best possible model and hyperparameters for a task, that's also an RL problem. Right? It's called neural architecture search, and there are several types of that. You can go through that. That's actually the main thing I'm interested in, and that's how I got into this, in search of neural architectures. So yeah, that's it. This is not very hard to learn. All this is very simple math. I think uh, if if you have an engineering background, you can easily pick this math up. It's not a big deal. As I've shown you, just understanding these things and knowing how this impacts your model is nothing very fancy, like going very deep, like understanding every single equation. No. Yeah, I hope this session was at least useful for some degree. I'm very sorry for the inconveniences caused because of the internet glitches. So you can leave all your comments in the feedback form. I think they will give you. It would be a great help if you would also star my GitHub repo that I've showed you. Yeah. Thank you so much for attending.
Okay. Yeah,
Thank you so
thank you,
much.
Abhi. Thank you for your wonderful session. I think this reinforcement learning is not as traditional machine learning or deep learning. So we need a little bit of different take on the learning part and the work part and the coding part and all. So I think like definitely we will share out all the best resources online for getting started with reinforcement learning and neural structure learning, because the supervised part on the linear regression or some traditional algorithm, the point is kind of saturated. Like the next leap is going to be like kind of quantum AI or reinforcement learning, neural structure learning, or some kind of graph learning algorithm stuff and all. So we will be having more such sessions in the upcoming days. So stay tuned with our meetup and social media pages so that we will post out all the resources and events. I think most of you are from our WhatsApp groups, so I think it's an active group. Like we will share the resources over there as well, right? Yeah, thank you for staying with us. Thank you everyone. Stay safe, take care of yourself during this good times, and again thank you so much. Bye bye, take care. Yeah, thank you, Abhi.
Thank you, Namudi bro.
Yeah,
Thank you so much for this opportunity.
thank you.